Okay, so when we're working within what's called the binomial distribution, which is that distribution we learned about in chapter 5, where every result could be broken down to a success and a failure, and say we did 50 trials, and we wanted to know what's the likelihood or probability of getting 40 successes out of the 50 trials, or getting 20 or getting at least 20 successes out of the 50 trials. That binomial distribution had a long calculation to do, and it would take a while. We did learn how to use a calculator. If you were in class, you should have learned that. But for a long time, we did this without having access to that. And so when we talk about doing these calculations without access to a nifty calculator, that binomial distribution takes a while to do the calculations on. So there is an approximation that we can do using the normal distribution. And so we're going to approximate using the same processes that we've used with our other normal distributions. The value, the distribution size, the sample has to be large enough. So for instance, around 100 or even 50. Sometimes they get really difficult to do, and so we can do the approximation if the following things are true. The number of trials times the probability of success, NP, must be greater than or equal to 5. And the number of trials times the probability of failure, NQ, must also be greater than or equal to 5. Remember, P is the probability of success and Q is the probability of failure. Because of the fact that normal distributions are a smooth bell curve that's continuous, but a binomial distribution would be broken up at, how many 8s were there? How many 9s were there? How many 10s were there? And because there's this gap between them, we have to take the data from the normal distribution and assign it to one of the two columns. And so we split these in half, and we do what's called a continuity correction by adding those values towards the 9.5. So for instance, if I want the probability of getting 8, I would have to look all the way over to 8.5 and all the way to 7.5 in order to say all that data belongs with the 8. We're going to pull that data together to correct for that. When we're doing a correction for continuity, there are different versions based on what our original situation is. If it's an equal to bar, then we want to reach out in both directions and include anything that's really close to A. So you'll notice we do everything from A minus 0.5 to A plus 0.5. That's the 8. If 8 was the middle value, we'd say anything from 7.5 to 9.5. When we have greater than and equal to, the calculation will stay greater than, but we're going to minus a half off of our A value. The way that looks on a bell curve, if you want to think about it as here's, say, A. If I want greater than or equal to the A, that's really this direction, but I want to make sure that A gets included. So to do that, I go back a half of a unit, and I shade from there to the right. So in order to include the value of A, maybe it was 8, I would slip back to 7.5 and then measure from there. But when I don't want A included, right here in my A is greater than, then notice we keep it greater than, but we add 0.5, meaning that instead of starting on the smaller side, we say, I don't want to include this A, so I'm going to come over here and draw my line half a unit beyond the A and shade to the right from there. So I'm omitting the value of A, whatever that number is. In any situation, and so it's the same thing with less than, equal to, and less than. You can see those calculation adjustments here. In either case, the mean is going to be n times p, and sigma will be the square root of npq. That's the stuff that we learned back in chapter 5. The last thing you need to know, so we have this set of steps that we're going to go through, and I'm going to try to walk you through them. The first thing that we do is we find out if it's possible to use a normal approximation. The way we do that is NP, is it greater than or equal to 5? And NQ, is it greater than or equal to 5? That's how we check, okay? The mean, if that's true, then we go to step 2. The mean will be equal to NP, and the standard deviation is the square root of NPQ. Oops, NPQ. The calculation that we saw above. We're then going to write the problem in probability notation. The probability of X And then this, I'm not sure what will be here. It'll depend on the problem. Am I greater than? Am I less than? Am I equal to? That's where we'd fill that in. And then we would rewrite it with the x. There's a symbol here. And then we'd either add or subtract 0.5 for the continuity adjustment. Maybe I add it, maybe I subtract it. We use the sheet up above here to determine how do we adjust for continuity. And then we find the corresponding z-values and we use the chart. Okay, this is all chart stuff that we would do for finding the probabilities for that set value. For z, it's the same as what we did in 6.2. We can use the same exact formula. This is not a sample. This is a specific result. Likelihood of getting 13 yeses. That is a specific result. And so we get to use our individual z-value calculation. All right, let's take a look at an example and see if we can walk through the process. Along the way, I'm going to be writing down some useful information. It says a magazine has reported that 6% of American drivers read the newspaper while driving. That is the probability of success, we'll call it, because we're trying to figure out how many people read the newspaper while driving. Okay, so P is 0.06, which default means that Q must be 0.94. Remember, they have to add up to 100%, success and failure. While driving. If 300 drivers are selected at random, that would be the size of my sample, and then find the probability that exactly 25. So X would be 25 exactly. All right, so we need to go through the process. The first step is to see whether or not this is a valid calculation. N times P would be 300 times 0.06, which is 18, and N times Q would be 300 times 0.94, which if we put in the calculator is 282. Both of those numbers are bigger than or equal to 5, so I'm okay to go forward. The next thing I need is the mean, which is always going to be NP, so it's 18. And I need the standard deviation, which is the square root of N, 300, times P, 0.06, times Q, 0.94. All of that inside the square root. So we'll grab our calculator and we will do the square root of 300 times 0.06 times 0.94, and we get 4.113. At this point, I need to write the probability and make the adjustments. I want X to be exactly 25, and if we look at the adjustment for exactly 25, it says if it's equal, then we do in between 0.5 lower, 0.5 higher. So we're going to go up and down both directions for this. So this will end up being the probability that 24.5 is less than X is less than 25.5. So if I were to draw a normal distribution curve, 18 is right in the middle, 24.5 would be around there, and 25.5 would be there. And I want in between those. So this is one where I have to do two z-scores and then find the difference, or find the middle. Okay. So I need the z of 25.5 and I need the z of 24.5. For the 25.5, we'll take 25.5 minus the mean of 18 divided by the standard deviation of 4.113. For 24.5, we'll do 24.5 minus 18 all over the standard deviation of 4.113. These need to be calculated. 25.5 minus 18, and we'll divide that by 4.113 and get 1.82. 1.82. And if we do the same calculation for our second, it's 24.5 minus 18 divided by 4.113 is 1.58. I'm going to go down a page to give myself some room here. And I'm going to have to go to the table at this point. 1.82, positive table. 1.8 is here. 00, 01, 02 would be 96.56. So I've got 0.9656. I have to subtract. It's always right minus left. 158. 1.5 is right here. And if I go over to 8, that would put me right there, 9429. 9429. Now if I subtract those, 0.9656 minus 0.9429 is 0.0227. And that is the probability of being between those two values. Or the probability, rather, of getting X. This is the approximation of getting 25 results. 25 yeses. Okay. The other one we've got members of a bowling league, 10% are widowed. So that means my probability of success should be 0.1. Probability of failure is 0.9. If 200 bowling league members are selected, that means N is 200. And my X, it says find the probability that 10 or more. So I can be bigger than 10, but 10 does work, so I'm going to use an equal to bar there. That's what we're shooting for. X to be greater than or equal to 10. So real quick, doing my check, NP is 200 times 0.1, which equals 20, which is definitely bigger than 1, and NQ would be 200 times 0.9, which is 180, definitely bigger than 5. So my mean should be 20, and my standard deviation is the square root of 200 times 0.1 times 0.9, or a standard deviation of square root of 200 times 0.1 times 0.9 is 4.24. And so my probability setup is X should be greater than or equal to 10. And for continuity correction, X will be greater than. Because I want to include the 10, I need to go before the 10. You can go back and check the chart. But for greater than or equal to, we get greater than, and we subtract 0.5. So we're going to go back down here, we're going to subtract 0.5, and stay with the greater than symbol. So instead of 10 here, I'm going to use 9.5. That's going to allow me to find my z-score for the 9.5 by doing 9.5 minus the mean of 20 divided by 4.24. To find that z-score, you can calculate 9.5 minus 20 and divide that by 4.24. We're going to get negative 2.48. Negative 2.48. Now, when we go to draw the distribution, remember that if what I'm looking for is the right-hand side, one quick way to find it is to change the sign and go the opposite direction, because that right side will be the same as the left side of positive 2.48. So rather than doing negative 2.48, getting the left side and subtracting that from 1, I can just go to the chart with a positive 2.48. 2.4, come over to 8, it's a 0.9934. So the answer for what's the probability of being to the right of that? It should be 0.9934. All right, so that's how we can use the normalization to do binomial distributions with approximations. All right, good luck, guys. We will see you in class.